Okay, let's start. We are in the chapter on supersystem transitions. That means transitions where you go from a number of systems to a higher order system that we call a supersystem. And the main mechanism is what we call a bond. You have two components, A and B, and somehow A and B are moving, varying the one relative to the other, and they reach a state where they are bonded. That means that they can no longer move freely, they are somehow attached. So more generally, a system is a collection of subsystems, but these subsystems are not independent. We spoke about the difference between a system and an aggregate. An aggregate is just a collection of loose objects, like people walking over a lawn. A system is a collection of components that are mutually dependent. That means there is a constraint. They can't move just freely. They are dependent on what the others are doing. There the example was a football team. The people in a football team have certain constraints about how they interact with each other. For example, they pass the ball to members of the same team, but not to members of the other team. So let's go into a little bit more detail about what that implies. So you create a system when you take a number of components, you create some kind of a bond, you couple them so that they are in some way dependent on each other. One of the things you get is that now you have a whole that is more than the sum of the parts. In what respect is it more than the sum of the parts? It's something we introduced in the chapter on systems theory. The whole has emergent properties. That means properties that exist at the level of the whole, but that do not exist at the level of the parts. Let's take a very simple example of such a system. I have often used this example of billiard balls. So imagine that you have two billiard balls, 1 and 2. Each of the billiard balls can move freely over the billiard table. That means it can move horizontally in the x direction, it can move vertically in the y direction. And now you create a bond. That means you attach one ball to the other. For example, in this way. Or, more simply, you could just put a little bit of glue so that the one is glued to the other. Now, what's the difference? Now you have this thing here. It can still move horizontally or vertically on the table, but the two balls can no longer move relative to each other. They are stuck to each other. They have to stay together. What they can still do is that this thing here can move rotation. It has a new type of property, which we call direction of orientation, which we can, for example, represent by this angle alpha. So the thing can rotate around this angle alpha, and it can move as a whole, vertically or horizontally, but the two balls can no longer move separately. So here we have a system that has this emergent property of orientation. Now, why is that important? If we think about chemistry, which is one of the typical examples, a molecule is a composed system consisting of atoms. Now, if two atoms are connected to each other like this, of course, that's a very concrete representation. When you look at the quantum level of the atoms, it doesn't look that neatly. But roughly speaking, these atoms are in a particular orientation relative to each other, and they are at a particular distance to each other. So the molecule can rotate. Why is that important? Because often in a molecule, the two atoms do not have the same charge. So the whole thing can be neutrally charged, but the one atom is more positive, the other one is more negative. For example, the electrons, which are shared by those two atoms in a molecule, if there are more electrons moving to the one atom, that atom will become more negatively charged, and the other one will become more positively charged. If now you put an external electrical field, the molecule will orient along that field. It's a little bit like that example we saw much earlier about magnets. The little magnets orient themselves according to a magnetic field. The same with an electrical field. If you would put an electrical field, all these molecules would orient themselves. If you look at individual atoms, there is no such thing as an orientation. An atom looks the same from any angle. The same with a billiard ball. A billiard ball doesn't have an orientation. No matter how you turn the billiard ball, it's always the same billiard ball. But if you attach two billiard balls towards each other, now they get this emergent property of an orientation, which can have all kind of interesting implications. Yes?
Is that not because of asymmetry, because of Pauli's electron law?
It depends on which atom connected to which atom, but typically one atom will tend to attract more electrons towards each other. But of course, if they are two the same atoms, for example, two oxygen atoms, you have the O2 molecule, well, then normally they will both be equally charged. But for example, H2O, the molecule of water, it's not symmetric. So it will tend to orient itself, it will tend to react to electrical fields, and you will tend to have the hydrogen atoms react differently from the oxygen atoms. So emergent properties are the properties that appear when you coupled two components to each other, and through that couple they develop a kind of a relationship. And that relationship wasn't there before they were coupled. So it is that relationship that now shows new kind of properties. It reacts differently as a whole than it would react if it were just the two separate things. I'll now go to another topic, which is again with an asterisk, which means it's a less general, less important topic, but it's interesting to know. It's what I call closure. So imagine you're starting with individual components and you couple the one to the other. Now the question is there a limit to the amount of components that you can connect to each other, that you can create bonds to each other? Well, if we look at molecules, sometimes there is, sometimes there isn't. Let's take the H2O molecule of water. That needs two atoms of hydrogen, one of oxygen. So it looks something like this. If this is the oxygen atom, here is a hydrogen atom, and here is a hydrogen atom. The hydrogen atoms are smaller, and it's asymmetric. But H2O, potentially you could make H2O2, hydrogen peroxide. But then basically you can't add more. On the other hand, typical example, organic chemistry is chemistry built around carbon atoms. And carbon atoms have the property that it's very easy to add more atoms to them, and you can go as much as you want. I'm not going to go into the chemical details, that's not the point. The point is, here we have what is called a polymer. A polymer is a molecule with lots of different components, and there's not really a limit to how long a polymer can go. Like the DNA molecule that is in our cells that contains our genetic information is one huge polymer. It's the famous double helix. The double helix can get as long as you want if you would be able to stretch the double helixes molecules that are inside our chromosomes. I think it would be hundreds of meters, if not kilometers, that are inside each cell. So, what is the difference between those where you can't add more and those where you can add more? So the concept I introduced, it's a little bit more an intuitive concept, is the concept of closure. So imagine that we have this kind of chain of carbon atoms, and here normally there are hydrogen atoms, but out of convention these are not written down because there are too many of them. But suppose that we make these carbon atoms like this. We can build them in principle in a closed loop. This is called a benzene molecule. It's a different chain from this thing that where you can just add things and add things and add things. Imagine a chain that consists out of the typical components of a lock. You can make one long chain, but you could also make the chain close in on itself. For example, if you want to make a chain to hang around your neck, you would want to close it. So, what's the advantage and disadvantage of this closure? Closure means that instead of attaching things at the end, you attach the end to itself so that there is no more space to add more things. On the one hand, that means the closed thing is clearly finished. It's kind of a system that has kind of a boundary. You can clearly see what's inside and what's outside. On the other hand, if it's not closed, it means there is kind of an end that can grow and that can diminish, and you could add links to the chain or you could take away links to the chain. So closure makes the system more closed in the sense of creating a clear boundary around what's inside, what's outside. While it is not closed, you can in principle continue adding things. I'll give you another example. Come on. So that's a benzene molecule. So these are little magnets, and magnets attract each other. Come on. I don't want to see these things. Always Microsoft. Oh. Well, hopefully those things will disappear at some stage. So I have a magnet, a north pole and a south pole, with a magnet always it's the north pole that attracts the south pole of another magnet and that repels the same pole. North repels north, north attracts south. So I could start having all my different magnets in one long chain, and I could continue adding here a node and there a node, and like that I could continue. Or I could put them like that in a closed circle, which means that all the endpoints are kind of used up. I could say that a system can go because it has certain junctures, certain endpoints where you can hook something else in. When all the junctures have been used, then it's when you get a closed system, and that's when it gets more stable. This thing will not fall apart as easily as this thing. Here, the ones at the end are pretty loose because they have only one point of attachment. Here, the whole thing is attached on all sides. So a closed system will typically be more stable, more well-defined, better separated from the rest of the world. But because of that also, it means it can't grow. While the ones that are open, they can continue to grow. There is no limit to how big the system can get. Some other examples. A marriage normally has two people in it. You cannot add a third person to a marriage. On the other hand, an association, for example, a student association, in principle, you can continue adding members to the association. So some associations, like a marriage, are closed. The two members of the marriage together fill up all the potential attachment points, while with an association you can continue to grow. Another example, a football team. In a football team, in principle, you have exactly 11 members. You can't add a 12th footballer to your team while playing a game. So, let's suppose that we have created a system by adding a number of components, coupling to each other so that the whole is stable. The coupling means that the different components to some degree depend on each other. They can no longer move freely. So now we have created a stable combination. If it's closed, it will be even more stable than if there is still space to add things or to take things away. That stable thing now, by definition of stability, it's fit. It will survive. Being fitted means now it will remain available. So we have built a system of a higher order that is stable, but that stable system as a whole can still interact, but it will interact in a different way. Because the normal interactions that attach the components of the system to each other, they have been, especially in a closed system, they have been used up, you might say. Now, if the whole thing wants to interact, it will have to interact via a different way. I gave this example of the two billiard balls that were attached to each other, but which can also be seen as a model of a molecule. So, if the molecule is, for example, positive charge here, negative charge there, I have created this kind of a closed system. But that kind of a closed system will interact with other systems of that kind. For example, imagine that there is another molecule, negative, positive. It will tend to align so that negative and positive attract each other, while positive and positive repel each other. So they will also interact, but they will interact in a more indirect way. Typically, they will interact via weaker forces. So they can still interact, but it's at a kind of a more fuzzy, more abstract level. And that is now a principle that we see in nature. If you go down to the smallest components, you see that their connections are very strong. Like the nucleus of an atom consists of quarks. These quarks are so strongly attached that basically you can't separate quarks from each other. On the other hand, the nucleus as a whole, which consists of protons and neutrons, you can separate, but it's very difficult. You need a particle accelerator, like in CERN. You shoot particles onto other particles with very high speed. You reach almost the speed of light. So you need an enormous amount of energy. You shoot them onto such a nucleus, and occasionally one of these nuclei will fall apart and separate into smaller particles. So at that level, the particles are very strongly connected. Let's go one level higher. An atom is a nucleus plus electrons. Well, the electrons can sometimes go away from the atom. We saw it already here in the molecule. Some of the electrons of this atom move to this atom, making it more negative. Electrical current, something you can get in metals like copper, electrical currents are electrons that have separated from the atoms and that can move freely. So getting electrons away from atoms is already easier. Next level, chemistry. We have different molecules that interact with each other. Well, chemical reactions happen all the time. Chemical reactions are ways where you take some components from one molecule and recombine them with some components from another molecule and you create a third molecule. Fire, burning, is a chemical reaction where typically the oxygen from the air combines with whatever is in the fuel to create new molecules, typically CO2. That's one of the reasons why we have global warming, is because each time you burn something, you're taking oxygen out of the air and adding CO2 plus water. That is a chemical reaction. These are relatively easy recombinations. Let's go to an even higher level. Let's say bacteria. Well, it's not that difficult to kill a bacteria, to take it apart. Maybe you heat it a little bit too much and the bacterium dies and it falls apart. Then it gets even easier. So each time you go up a level, the different components of the systems are less strongly attached. If you go to the level of a human being, well, basically you just need a kitchen knife to separate the parts of the human being. You don't need any particular chemistry or anything. Let's go to an even higher level, to a group, to a society, to this class. Well, it's not very difficult for me to separate the students in this class. I just ask, will all the ones whose name starts with an A sit there, and all the ones whose name starts with a D sit there? Separating them costs very little energy. So that is what we see as we go higher up to super systems of super systems. The bonds become weaker. And then we come to this very interesting concept, which was proposed by somebody that I very much admire, Herbert Simon. Herbert Simon is one of the fathers of complexity theory, one of the fathers of artificial intelligence. He also got a Nobel Prize in economics. He got very big awards in philosophy of science, in psychology. He was kind of a universal genius. So he has one very interesting paper called The Architecture of Complexity. So, and what he did was he argued why complex systems have this particular kind of organization, an organization we will call hierarchical. So let's show it more. Oh, why can't it just show me the slide? So suppose I start with a number of loose components. The loose components interact with each other and they get bonds. They get attached to each other and then these bonds stabilize and I can kind of get higher order systems. So let's go further. And now I can continue this whole story and building up things higher and higher. Small things here group themselves in slightly larger systems there, group themselves in slightly larger systems there, group themselves in slightly larger systems there. That's the way it evolves. Now, if I'm a scientist and I want to understand the system of that level, I can go downwards. I can decompose the system and say, well, that big thing there, for example, this big organism consists of different organs, and these organs consist of tissues, and these tissues consist of cells, and these cells consist of organelles, and these organelles consist of macromolecules, which consist of molecules, which consist of atoms, which consist of nucleons, which consist of elementary particles, etc. So what I'm doing is I'm starting from the top and I'm decomposing. Now what Simon said is that's a strategy that works to some degree, but you lose the emergent properties. So systems theory would say, well, you have to look at the higher order system, you have to look at the whole to understand it. A reductionist approach would say you have to decompose it, you have to analyze it into its components to understand it. What Simon was saying, well, both are right in a way. But going down has the advantage that going down, you are going to the more stable parts. Because the more stable parts have these stronger connections, they don't fall apart as easily. So they are, in a sense, easier to understand, they are easier to grasp, to see what the properties are. That is why physicists try to go as deep as possible by shooting particles at extremely high energies onto other particles to see what is in there. So he calls these systems nearly decomposable. So you can decompose them, but you're losing something. So they're not really decomposable, but decomposing it is a useful strategy, especially if we decompose from very high. Well, if I want to decompose, let's say, the system VUB, I might start by being a very rough separation and saying there are the students, there are the professors, there are the administrative personnel, there are the assistants and PhD students. That's one rough decomposition, and then within those I can start distinguishing between faculties and between departments, and then I can start looking at individual people. I can decompose that because each time the lower level is more stable, is more reliable. Like, okay, I can decompose a VUB into professors and students, but some of these students become professors, and some of these students leave, and some of these professors move to another university, and new professors come in. It's not very stable. But if I decompose it to the level, let's say, of one particular professor, that professor may move from one university to the other, but the professor is not going to change as quickly as the positions that the professor has, or that the activities that the professor has. So the near decomposability means by decomposing, the advantage is you get components that are kind of more solid, that are kind of more stable, more reliable. But you should not forget that the whole still has properties that the parts don't have. These are the emergent properties. Yeah.
Can we really say that smaller systems are more stable? When to me it seems like molecules change on a much smaller time scale than, for example, I don't know, planetary systems or even ecosystems. It seems like the amount of time you have for observation before something changes is much larger with a larger system than something relatively large changes.
That's a very good remark, because in some respects it's true that the higher order systems are more stable. Like you say, if you look at me as a biological system, my metabolism is constantly turning one molecule into another, while I remain the same. So there is an aspect there indeed that Simon did not look at, and that is the aspect. Well, we wouldn't really cover it in this course, but the aspect of autopoiesis. That means that you can have systems that are dynamic, that are constantly changing, but in such a way that they keep an identity. So the conclusion of this chapter on supersystem transitions, is we have this phenomenon. You start with a number of loose components, they interact, they tend to form bonds, the bonds tend to stabilize into systems. These systems now, in the same way, interact, and the whole process starts anew. So you repeat this thing, and you get this hierarchy of systems within supersystems, within supersystems, within supersystems. That is one form of complexification. We said complexification means differentiation and integration. Differentiation means that within this mass of things that are more or less the same, I start making distinctions. I start drawing boundaries. I start to say, these here are separate from these here, and therefore I group them differently. That's differentiation. Differentiation between these things, but integration inside them. Because these things now are more dependent on each other, they are integrated. So that process is the simplest form of complexification. You differentiate at one level, you integrate at another level, the two together add complexity. But this is a kind of a complexity that I call structural. Structural means that these are bonds that are kind of stabilized, they're kind of rigid. They are what we call constraints. A constraint is something that reduces the freedom. The system, when it undergoes this kind of supersystem transition, it has lost freedom. These things can no longer move separately from each other. They are grouped in those compartments, they cannot move freely anymore. Now, when we think about complexity, there is this kind of structural, rigid, stable complexity, but there is also another type of complexity, the complexity where things become more dynamic. And now we're going more in the direction of what you're saying. That is that if I think, for example, about intelligence, mind is much more fluid, more adaptive, more dynamic than, let's say, a rock. A rock, that's structural complexity. All the molecules in the rock are rigidly connected. They don't move anymore. If I think about what's going on in my brain, there are constantly billions of activities in the neurons, electrical currents that move from one neuron to another. My feelings, my thoughts, they're constantly moving. So that kind of complexity now, we need a different concept to catch it. Concept not of a supersystem transition, but what I will call a metasystem transition. So let's define what a metasystem is. So let's go back to evolution. Evolution is variation and selection. Selection means that you become fit enough to survive. In order to be fit, you need to be adapted to your environment. Now, adapted to your environment, it means that you have found a niche, means a particular way of life within your environment where you fit, where you get everything you need. One of these subsystems that gets integrated into a larger system, you might say it has found a fit, it has found a place where it's kind of safe, where it can kind of survive as such. But that assumes that your environment is not changing. Fitting in a particular place assumes that that place is more or less the same, that you fit in because you have the right configuration for these kind of conditions. But what if the conditions change? And that's what we typically see in real environments. Conditions change. Things that are fit in one circumstance are not fit in another circumstance. Let's take a biological example. Snow hares live in Arctic regions where there's a lot of snow, so they are white. They are white so that it's difficult to be seen by predators, like, for example, foxes that would otherwise easily see the hares, kill them, eat them. So being white in an environment that is covered in snow is a way of being fit. But now suppose that the snow melts, a white hair on a brown soil will be very visible. So the white hair that was well adapted to the snow is no longer adapted. So what happens if it's a long-term process? Let's say that because of global warming in the region where there was always snow, there is no longer snow. Well, all those hairs that are the whitest will be the first ones to be eaten. So those that are maybe a little bit less white may survive a little bit longer. And if over many generations, the hairs will evolve to become brown so that they're no longer visible. But that's a very slow process. Imagine that we're speaking on a shorter time scale. In winter, everything is covered in snow. In summer, all the snow is gone. Well, there could be another way to solve the problem. That is that in winter, the hares have white hair. As spring comes, the white hairs fall off, great brown hairs go instead. So in summer they are brown. In autumn, their brown hairs again fall off, white hairs go, so that by winter they're again white. Some creatures indeed do that. They change color in the season. But that is in the case that the changes in the environment are predictable. Every winter there is snow, every summer the snow goes. It would, of course, be more interesting if you could change on the spot. And there aren't many animals that can do that, but one of them, the famous one, is a chameleon. Chameleon can change its color depending on the background. So I suspected that these photos are photoshopped, but just to show you, but there is a more interesting case, that these squids and octopuses, they can change color in a much more spectacular way even than chameleons. Let's hope that the video will work, which of course it doesn't. How can I tell my PowerPoint that it should consider this as a link?
Yes.
That interface changes for no good reason. I don't know how to make a presentation out of it. Maybe here. Could it? No. No, that's not. Tell us what can be better. There's a lot I can tell them that can be better. No, I don't want to share it. I just want to show it. Apparently it doesn't want me to show. anything. Okay, so I'll just tell you what's in the video. You can probably find it on YouTube. Look for an octopus changing color. Octopi and squids, which belong to the same family more or less, they have in their skin, they have pores where there are chromatophores, I think it's called, cells that can put in pigments, and depending on where they are, they can show different colors. And they can really not only change the overall color, they can change the pattern. So in the video you've seen it, for example, if the octopus is over smooth sand, it gets smoothly gray. If then it gets on a piece of coral, it gets black and white dots that look like the pattern. And some octopi can change in all possible colors and even their shapes. They are extremely adaptive. So it is this concept of adaptivity that I want to speak about. Adaptivity, we can define as being able to change your present condition depending on the condition of the environment. So if the octopus is in between, let's say, green seaweed, the octopus may become green. If the octopus is on rocks, it will create a kind of an irregular pattern of light and dark. If the octopus is in a hole where it's dark, it will become black, so that it's not visible. That is an example of what I call adaptivity. So adaptivity is an example of a concept we saw before, the concept of control. So that's a reminder of what we saw in the chapter on cybernetics, a control system, which I call here an agent. What's inside the circle is the system, what's outside the circle is the environment. The agent perceives what's in the environment. So, for example, the octopus perceives that it is on grey sand. It acts so as to reach its goal, and the goal of adaptivity is to be fit for the environment. In this case, the goal of the octopus is not to be noticeable in a particular environment. What's the action of the octopus? It will open or suppress certain chromatophores, certain of these colored cells in its skin, so that, for example, it becomes more dark in some spots, more grey in other spots, more reddish in other spots. It will act. The environment, if the environment is static, that's all it needs to do. It needs to fulfill the right, it needs to get the right color pattern. But if the octopus is moving, or the environment is moving, for example, there might be a shadow that comes over the octopus. In this case, when the shadow comes over the octopus will automatically become darker so that it's more fitting in with the shadow. So the perturbations, these are the changes in the environment. Perturbations is what makes the system deviate from its goal. Its goal is not to be noticeable. Its goal is to blend in with the environment. When the environment changes, the octopus will perceive that something has changed. So it needs to have eyes. It needs to see clearly what shape and what color the environment is. Its action is, again, to change these pigments in its skin so that it's adapted. So this is a very important scheme, the scheme of adaptivity. Whenever something changes in the environment, the system acts so as to compensate for that change so that it remains in its fit condition. It wants to be in the condition where it is adapted, where it is fit. Okay, so here's a good moment for having a 10-minute break. Can switch it off?
Pause it?
Yeah, pause it, yeah. So you see really how the colors completely change wherever he goes.
Someday the ship on the ground, wake up where the clouds are far behind. We will travel just like landing drops, high above the chimney top. That's where you find me, oh, somewhere over the rainbow. Bluebirds fly, and the dream that you did to oh why can't I see trees of green and red roses too. I watch them move, me and you and into myself. What a wonderful world. The lassie skies of blue and I see clouds of white and the brightness of day. I like the dark and think to myself, what a wonderful world. Bright colors of the rainbow, so pretty in the sky, are also on the faces of people passing by. See friends shaking hands, say, how do you do? They really sing.
Okay. So now we come to the notion of a meta-system. In the chapter on cybernetics, we saw that you can have a control system and then you can have a control of the control. So the classical example of the control system is a thermostat. A thermostat is programmed to reach a particular goal, which means having a certain temperature in the room, let's say 21 degrees. The thermostat will achieve that temperature by perceiving what the temperature is, acting by either switching on the heating if it's too cold or switching off the heating if it's too warm. The perturbations are all the changes of temperature in the environment. The thermostat will keep at its goal to keep the temperature at 21 degrees. But now we saw you can build a second control system on top of the first. And the second control system, what it does is it specifies the goal of the lower order system. So the goal was 21 degrees, but suppose that we want to save energy and instead we want a smarter thermostat, one that gets 21 degrees when there are people in the room, but 16 degrees when there are no people in the room in order to save fuel. So you could have a sensor, an infrared sensor, that notices when people enter the room. It then switches the goal of the lower level system and makes it from 16 to 21 degrees. When the people leave the room, it switches back to 16 degrees as a goal. So that is the idea. The goal at the lowest level, goal 1, is actually the action of the system at the higher level. Another way to put it is goal-directed systems use what we call conditioned action rules. If a certain condition is present, then it performs a particular action. In the case of the thermostat, condition temperature lower than 21 degrees, action switch on the heating. Temperature higher than 21 degrees, action switch off the heating. These are the inbuilt rules of the system. What the higher order system does is it changes these rules. So if here the rule was temperature smaller than 21 degrees heat, the higher order system will change this temperature. If people in the room set 21 degrees, if no people in the room, set 16 degrees. So that higher order system, we call it a meta system, it's a level higher than the control system. So a meta system generally we define as some system that controls some system at a lower level. The system at the lower level we call the object system. The control system controls the object system, and the two together form a meta system. But now I can put a control on top of the control, and then I have a meta system. So the formula is meta system is control of object system. And then a higher level is a meta system. Is control of meta system. Now, why would we want to have a higher control level? Because the control at one level uses these fixed rules. Fixed rules are rigid, they cannot adapt. The rules can adapt to a change in temperature, but they cannot adapt to presence or absence of people. So you need a higher order system to change the rules. So the meta system, each meta level makes the system more adaptive. It's less rigid. It can adapt its rule to more different circumstances. It can adapt rules and adapt the rules for the rules and the rules for the rules for the rules. So in that sense, adding a meta level makes the system more adaptive. That means fitter. What it especially does, it increases the variety of the system. We saw the variety is the range of all the different things that the system can do, all the different actions. The actions that the system can do are normally constrained by these kind of rules. There are certain rules that say you can do these actions in these circumstances, but not these other things. Adding a meta level, in principle, expands your state space, allows you to perform a wider variety of actions. So what you get is something like this. A meta system transition means you add a meta level, if you are at level 1 and you add a next meta level so that you get to level 2, your variety increases. If you add a further meta level, you even more increase the variety. So that is a very kind of a general description of large-scale growth in complexity during evolution. We will see examples of how this has happened in evolution, but the general idea is you start with a system that can do a number of simple things, always the same, and then you make it more flexible, more adaptive by allowing it to change the things it does depending on additional context conditions, additional things. So, at first sight, adding a meta-system level makes the system more adaptive, smarter, flexible, better able to deal with all kinds of different circumstances. So, you can understand why evolution would tend to add these meta levels. But there are also disadvantages. So there are advantages and disadvantages. The advantages, in principle, you get a wider range of things you can do, you become more adaptive, you add the variety, your capability of reacting to different circumstances. But now we have to look at what are the disadvantages. So let's assume that I saw the scheme, I built one control system on top of another control system. So here I have done it that goal is here in the middle, but if I shift it a little bit like that, I can just put one on top of the next one, and then on top of the next one, and then I get something like this. There are always the perturbations, there's always the perception, there are the actions, but then I build things on top of things, on top of things. Now you immediately start to see what's the problem there. In principle, the goal at the top level is the overall goal, the one that kind of controls everything. And at the different levels, there are more specialized goals. Let's take the example that we also saw in the context of cybernetics, a lion. At the top level, the goal of the lion is to survive and reproduce, fitness. A level below, in order to be fit, the lion should eat. Whenever the lion is hungry, it should satisfy its hunger. In order to satisfy its hunger, it needs to hunt. Next, lower level, hunting. At the level below, it needs to choose a particular prey, for example, a particular zebra, and to run after that particular zebra. Once it has come close to the zebra, it needs to bite, so it's a specific place to kill that particular zebra. So we go from a very high level abstract goal, survival, to a very low level concrete goal, biting in a particular place in order to kill the zebra. So you have this whole hierarchy of goals. Each time you go up, it gets more abstract. But imagine that you would, for each action, have to check the top level goal. For each movement that the lion would do, it would have to check, is this the right action for survival? Yeah, that would make the whole thing pretty complicated and pretty clumsy. Because the perception, the information about what's going on, needs to go up, and then the decision needs to go down. Each step takes time. Each step, there's a possibility of misunderstanding. Some information here that doesn't reach the next level. Some information going down there that's misunderstood. You can see what are the problems. And we see that best in a different type of control systems, in bureaucracies. Human organizations typically have this hierarchy, a control hierarchy, where let's say you have a multinational firm, and at the top there is the CEO, Chief Executive Officer, and below that there are lots of different managers. Or you look at it in an army, at the top there is a general, and under the general there is a colonel and a major and a captain, etc., up to down to the level of the soldier. Typically in human organizations there are lots of different levels, and imagine that in the war, a soldier thinks that there is somewhere there an enemy in that house, and then decides to go and explore that house. Should he get the permission of the general? Well, obviously, if he would have to wait until he gets the permission of the general, it would never work. So, going up all these levels, going down all these levels has these advantages. Ideally, you would like that the lowest level can make as many decisions as possible. And that is something that we see in societies. There is a trend in flattening hierarchies. Social systems like ministries, big corporations, armies, they have typically lots of different levels. But it creates a lot of bureaucracy because these messages need to go up and down the levels, and the more steps that are involved, the slower, the more mistakes, the more complicated. So it's one of the things that I have learned in management. It is that try to reduce the number of levels, because then most decisions can be made only at level 3 and you don't need to go up to level 5. But can you do with less levels? The reasons we had levels in the first place, the meta-system principle, is that decisions at this level are pretty rigid, because at this level there's not enough information to know to take everything into account. So the higher level typically has more information, knows more. The higher level can tell the lower level what it should do. The sergeant tells the soldier what he should do. The lieutenant tells the sergeant what he should tell the soldiers. The colonel tells the lieutenant what should be done, etc. So when can you decrease the number of levels? If the lower levels become smarter, more informed, the more information the soldier has, the less he will need to check with his superiors whether he's making the right decision. And that is a trend we see in organizations, let's say, over the last 50 years or so, is they have learned that it's better to have the employees at the lowest level even already pretty autonomous, pretty well informed, so that they don't need to check for everything that goes on with all the higher levels. Now, that problem of too many levels, that means the problem of bureaucracy. In evolution, it doesn't really occur. Why is that? Because in evolution, adding a meta-system level is very difficult. You have a whole system of control rules, of conditioned action rules that functions pretty well. If it didn't function well, the system would have been eliminated a long time ago. So adding a level is something pretty unusual. It's pretty exceptional that a meta-system level is added in evolution. It will only happen when it's really necessary, let's say, when there is no way to expand the control at a lower level. Yes?
Have we seen a flattening of hierarchy within evolution?
No, because evolution works from the bottom up. It adds levels slowly and with lots of effort. While in human organizations, it's very easy to add levels. And there is a tendency to add levels because people in an organization want to be promoted, but in order to be promoted, there needs to be a higher level to which they can be promoted. So there is a tendency to always create more levels. So instead of having an army with 3 levels, let's say, soldiers, onderofficieren, how do you call that? like sergeants and officers, yeah, then you can't make much promotion if there are only 3 levels. So that's one of the reasons why in human organizations there tend to be many more levels than are strictly needed. In biology that doesn't happen because adding a level is a very fundamental change that needs to have lots of conditions that are quite right to develop this new level. Also, what we see in evolved metasystem hierarchies is that the lowest level does most of the work. If I look at my own body, if I put my hand on a hot plate, I will immediately pull it away without having to go to the highest level of conscious reflection. My conscious reflection would tell me, if you put your hand on a hot plate, you run the risk of being burned, so you should take away your hand from the hot plate. But that's not the way it works. The signal of heat via my nerves goes straight to my spine and to the nervous system in the spine, and it already pulls away the hand even before it reaches the brain. That's because these are kind of reflex action. We will immediately discuss what are these different types of levels of actions. That is so basic that if my organisms had not been organized like that in the very beginning, before there was anything like a brain, that the organism simply wouldn't have survived. So evolution, of course, makes sure that the lowest level is as efficient, as effective as possible before it adds a higher level. And there's a cybernetician who has formulated this as a law, a cybernetician called Heylighen, who called it the law of requisite hierarchy. You need hierarchy up to the fact that the lower levels can't do it on their own. If the lower levels are not sufficiently smart or not sufficiently informed to solve the problem, then they pass it on to the next level. If they just can't do it, then they pass it on to the next level. But requisite hierarchy, that means depending on the circumstances, the more control capability there is here, the less there is need to add level 2 or level 3. So let's now go into more details about the most fundamental metasystem transitions in the history of life. And now I'm referring to the work of somebody with whom I have collaborated for a long time, but who died about 15 years ago, Valentin Turchin. Who's a cybernetician that originally worked in the Soviet Union, but then emigrated to the US. So he actually developed this concept of metasystem transition, and he also had a particular history of life understood in terms of metasystem transitions. So let's start with the lowest level. He called it the simple reflex. A simple reflex, that's just a conditioned action rule. If that anemone, which is kind of the most simple multicellular organism, multicellular animal that you can find, if you touch that, it will retract. That's because the anemone does not want to be eaten. If some fish or some big thing attacks it, it retracts and makes itself as small and as compact as possible. So we have a very simple condition action rule. Condition, you feel that you're being touched by something. Action, you retract. How does that conditioned action rule function? Animals are characterized by the fact that they have nerves, and a nerve is a special type of cell that transmits electrical signals, and the electrical signals go from the sensor, the part that senses the condition, in this case being touched, to the effector, which is the part that performs the action, which is a muscle, and the muscle contracts. So it's a very simple anatomy. Sensors send signals to muscles, the muscles contract, the signal is an electrical charge. That's something that, by the way, that was discovered about 2 centuries ago by a scientist called Galvani, who did experiments with frog legs. The frogs were dead, so he had the legs and he was experimenting with electricity, and he noticed that when he put an electrical current on the muscles of these frog legs, the frog legs would contract. So that's actually what the muscle is. It's something that when it gets an electrical signal, an electrical charge, it contracts, and that's what a nerve does. A nerve is the part in your body that transmits these electrical charges from sensors to effector. So that's, let's say, the very simplest level. Just condition, just action. So let's go to the next level, which Turchin called the complex reflex. Reflex is if A then B. If my hand touches a hot plate, I pull it away. There's nothing complex about it. Complex reflex it's not just one condition, one action. It's a combination of conditions that leads to a combination of actions. And what you want is that these different conditions and actions are coordinated. To coordinate that whole thing, those nerves, instead of like in the anemone just going from sensation to action, they need to come together in some central part, which becomes the brain. So this is about the simplest brains that you can find. That's a so-called planarian flatworm. Very simple creatures. They have some very nice properties. For example, if you cut one in two, it just goes into 2 worms. So they have a kind of an anatomy. They're not purely symmetrical. They have the equivalent of a head. They have the equivalent of eyes. And the head can sense things. Now, why does this thing need a brain while the anemone does not need a brain? Well, anemones just sit there passively until something touches them. And if that something that touches them is small, they will eat it. If it's something big, they will retract and try not to be eaten. That's all anemones do. This thing searches for food. It can move. The moment that an animal can move, it needs to decide where to move. Do I move to the left, to the right? Do I move straight forward? That means it needs to sense what's around it. It needs to recognize the difference between, let's say, the sight or the smell of food, or the sight or the smell of a danger. So while that creature is crawling, let's say, somewhere on the bottom of the sea, on the left-hand side, it smells something that looks like food. On the right-hand side, it smells something that looks like a predator that might eat it. So its brain takes those incoming information, the smell of predator, the smell of food, together and decides you should move to the left. So these nerves will lead to muscles that make the whole thing move to the left. So that's the complex reflex. Instead of conditioned action, you take a number of conditions, you compare them, and out of this in the brain, you give different action demands to the different muscles. So there is no longer a simple conditioned action rule, there is conditioned action with combination of lots of different conditions. Then we come to the next level, the learning level. Now we're speaking about slightly higher animals, but here it's a rat. A rat is already a mammal. Mammals are already pretty smart. But the learning level we already see in relatively simple animals like snails and slugs. And then animals like octopi are actually pretty smart. What's the learning level? In the complex reflex level, you have still your nerves and signals. These signals come together in the brain. The brain combines different signals coming from different sensors and sends out different signals to different effectors, to different muscles. But in principle, it does it always in the same way. The learning level is that the rules that specify which signals goes where can adapt. The animal can learn on the basis of experience. So this is a so-called Skinner box that was developed by the behavioral psychologist Skinner to study learning in animals. What's the idea? The rat has a lever, it can push on the lever. If it pushes on the lever, something happens, and what happens can be good or can be bad. It can get some food if it's lucky, or it can get an electrical shock on its paw if it's unlucky. So the rat has to learn what is the right thing to do. And for example, in this case, there are two signal lights. Maybe the rat will learn that if the light is green and it pushes on the lever, it will get food. But if the light is red and it pushes on the lever, it will get an electric shock. And it turns out that this rat learns pretty quickly what is what. So how does that work? It works via what's called reinforcement. If a particular neural connection, so in the rat's brain, there is a site of the lever, there is a site of the green light. These two connections together lead to connections that make the rat push on the lever. It's a pretty complex process that's happening inside the brain. If that now is resulting in a positive thing, namely food, these connections will be reinforced. That means they will become stronger. That means that the next time that these same signals appear, green light and lever together, the rat will be more inclined to push on the lever. If the next time it again gets a reward, it gets food, it will be even more inclined to push on it the next day. So if the same thing happens, let's say 5 or 6 times, the rat will know whenever the green light is on and I push on the lever, I will get food. So that's a very simple mechanism. Reinforcement, if whatever connection in your brain led to a particular action and the result is positive, you do it again. Negative reinforcement, if the light is red and the rat gets an electrical shock, it will not push the lever. So imagine that first the rat learns that pushing on the lever gives it food, but up to now the red light was never on. And then the red line is on, and the rat, not knowing anything, will still push the lever, and now it gets a shock. It will very quickly unlearn to push the lever whenever the red light is on. So that's a way how we see that the conditioned action rules change. So in this case, let's say the rule originally was lever, push, and then food. But now this changes in lever plus green, push, lever plus red, not push. So what the learning has done is it has changed the conditional action rules. that is typically a meta-system transition. Something that was fixed, whenever you see a lever you push and you will get food, is changed into whenever the lever and the green light is on, you push, and whenever it's red, you don't push. So that now creates an enormous jump in variety. Previously, the brain could recognize a number of combinations of conditions and lead to a number of combinations of actions, but all these neural connections had to be inborn, they had to be instinctive, and it's pretty difficult for evolution to develop a very complicated network of condition-action connections that always gives the right result. Now you add this learning mechanism, and suddenly the brain can adapt to many more situations. It's an enormous increase in the variety of what the system can do. Now it can learn an infinite number of different kinds of situations. Well, that is one form of learning, immediate condition action. If the condition is there and you perform the action, you get a reward. There is also the more indirect learning, which is called Hebbian learning, instead of reinforcement. Hebbian, because it was first proposed by a psychologist called Hebb, which is that one condition tends to be followed by another condition. And there's another classic experiment that illustrated the experiment of Pavlov. So Pavlov was an early neurophysiologist who was studying dogs, and he noticed that when he gives a dog food, the dog salivates, so it produces saliva in order to swallow the food. But then he discovered that if he rings the bell just before he gives the dog food, the dogs would learn to anticipate that the bell would be followed by food, and the dogs would start to salivate even when the food wasn't there yet, because they had heard the bell. So that was not a condition-action rule, but a condition-condition rule. So the condition-condition rule would be something like bell, expect food, and if there is food, salivate. So the dog would already learn that the bell alone, it would already start to salivate. So that's a second type of learning. The reinforcement learning is that the action you perform, if it leads to a good result, it gets reinforced. The Hebbian learning is if one condition is followed by another condition, you learn to anticipate the second condition, and then you act as if the second condition would be there even before the condition is there, which is again a very powerful thing because it means you can anticipate lots of things. Your brain can see things that aren't there yet. So that is the level of the meta-system that we find in animals. Now we need to go to the level of people. What's the difference between people and animals in terms of intelligence? We're speaking about a qualitative difference, not a quantitative difference. It is that these rules, animals can learn them, but only if they experience how one condition is followed by one action or how one condition is followed by another condition. They have to experience the two together, otherwise they can't learn it. What people can do is people can reason about hypothetical situations, things they have not experienced, but they can plan. They can say, if I would be in that situation, then if I do this, then probably that is going to happen, and then I can do this, and then that will lead to that, and you can make a whole plan of things that have never happened and that may never happen. That is again a meta-system level higher. Instead of being dependent on different conditions happening, the one next to each other, we can reason about conditions that are hypothetical, or what philosophers sometimes call counterfactual, things that are not really there, but that could potentially be there. We can reason about counterfactual situations. Now, how can we do that? Because of language. Language, or more generally, the use of symbols. Why? Because a symbol represents a condition, or potentially an action, that is not there. I can, for example, tell you, what would you do if, let's say, a rabbit would enter the class? You can easily imagine a rabbit entering the class and thinking, what would I do? Maybe I would try to catch the rabbit, or you can think about hypothetical situations, because I have just used the symbol rabbit, R-A-B-B-I-T. It's a symbol, it's not an actual animal, but you know that it represents an actual animal, so you can reason as if there would really be a rabbit in the room. That is the higher level of control that Turing calls thinking. So we have the following levels: simple reflex, complex reflex, learning, and thinking. Each time a meta-system transition that makes the whole cognitive system, the whole ability to deal with different conditions much stronger, much wider, much more flexible. But now, could we go one level higher than the thinking level? So, where does the thinking level come from? As I said, mostly from language, but symbols do not only need to be words. Symbols could be mathematical symbols, could be computer programs, could be drawings, could be schemas. Thanks to symbols, we can conceive of situations that we have never experienced before and reason what should happen in these different conditions. For example, I buy some apparatus that I've never used before. What do? I look at the manuals that comes with it, and in the manual there are some drawings and there are some explanations. And by reading these explanations, I know that if I push on that button on the apparatus, then this thing will happen. And if I want to make that type of coffee with my coffee machine, then I should do these and these things. The symbols are what allow me to reason about situations I've never experienced before. But in order to use the symbols, I need to have learned the symbols. I need to have learned the symbols, the words, the meanings, and different rules that apply. That's what we might call cultural knowledge. Most of my concepts in my mind I have learned via culture, by going to school, by speaking with other people, by reading, by seeing things on TV, by reading things on the internet. I have collected all these different symbols representing different concepts. These symbols are connected by different kind of rules. I have not invented it myself. But where does the culture come from? The culture is a system that has evolved, but evolved the way evolution normally works. It means via trial and error, variation and selection. Whenever somewhere there was some new idea, maybe that idea was not as good as others, so it was forgotten, and occasionally there is an idea that's really so good that more and more people start using it, and then it becomes part of the general knowledge. So culture evolves, culture invents new symbols, new rules that help us to understand the world, but up to now, we might say that culture is something that is not there's no control system. Culture is not controlled. Culture is something that happens spontaneously, which means, like all evolutionary processes, it can develop very sophisticated things, but it's kind of slow. Evolution takes time. There's a lot of trial and error. Lots of ideas need to be tried out in different circumstances before you know which ones are solid enough that they would become a part of general knowledge. So what then would be the next meta-system transition, that this process of cultural evolution becomes controlled? And we already see that to some degree in certain aspects of culture. Science, for example, is to some degree a controlled development of new knowledge. Scientific method gives you a number of, we might say, meta-level rules of how to develop new knowledge. For example, one of the meta-level rules might be, if you have some hypothesis, operationalize it and do experiments to test it. If the tests do not result in what your hypothesis says they should be, abandon your hypothesis or refine it in this and this way. So the scientific method, in a sense, is a meta level. It's starting to become a meta level above the meta level of symbols, thinking and communication. So the general hypothesis, which Turchin and I and a number of other people have been working on, is that we are now in this kind of intermediate stage where we are developing this higher level of cognition above the level of thinking. And what are some of the components of that higher level? Well, the scientific methods. Philosophy is another aspect of it. Artistic experimentation, discussion, computers and internet, artificial intelligence, all of these are methods to try to go beyond this level of thinking in the sense of generating new knowledge in a controlled way. Yeah.
I'd say it's just a product of thinking, like it doesn't go beyond thinking.
What do you mean?
Philosophy, the scientific method, it doesn't go beyond
No,
thinking.
it does go beyond thinking because it questions the, let's say, what is typically about philosophy. Philosophy will take a common concept, let's say love, democracy, consciousness, and then try to understand what is that really? Is there really such a thing as consciousness? And then you come, for example, to give you an example I know well, the philosopher Ned Block has made a distinction between access consciousness and phenomenal consciousness. We don't have the time to explain the difference, but it's an important difference, and there isn't a word in the language for access consciousness and phenomenal consciousness until Ned Block invented that new concept.
He was thinking in symbols to develop that concept.
He was thinking in terms of symbols, but at the same time he was creating a new symbol. So it's kind of the beginning of a meta level. He was thinking about symbols rather than just with symbols. Of course, you have to start with something, just like those first planarian flatworms that developed the brain. They initially just had nerves that didn't come together in one central part, so they had to work with the nerves. But when those nerves started connecting in such a complicated way that it became something like a brain, yes, you might say that they had gone to the higher level. In the same sense, you might say that philosophers who question concepts that everybody uses and who reformulate them into new concepts, more precise concepts, they are in a sense moving toward this meta level. Yeah.
And that would then be thinking in group of the same hypothesis, or what? But I don't understand how we would call this verb. Simply, what do you do when you're meta thinking? What are you doing? I don't know what you're doing when you're meta thinking. Is that an interaction between multiple people that have some intersubjectivity in thinking, or what?
Intersubjectivity is definitely one of the aspects, but also working with data, working with computers, experimenting. So there are different things that help you to go to that meta level, but we can't yet say that there is one neatly defined meta level, but we are moving there. That's why I call it's an ongoing transition.
Yeah.
If the transition was finished, I could tell you exactly what is needed. Now I can tell you, here are some steps, some elements of the transition.
Like the use of semiotics.
Could be, semiotics definitely is a kind of a transition.